Hello students, in the previous class we have seen the isomerism nomenclature, and today I am going to explain you about the bonding in coordination compounds. That is nothing but in this we are having four metals, that is valence bond theory and crystal field theory, ligand metal bonding theory and molecular orbital theory. So this generally Werner's theory and Sidgwick theory will also explain the bonding, but they will not give current explain about the geometry and hybridization. So to overcome that, there are four modern theories, that is valence bond theory, crystal field theory, ligand metal bonding theory and molecular orbital theory. So now let us see the valence bond theory. So coming to here, bonding in coordination compounds. So bonding in coordination compounds is nothing but what here, in coordination compounds, how the bonding is going to happen. So generally bonding, how it will happen, by combination of atomic orbitals, or we can say here SPDF blocks. By using this, the bonding will happen. So there are four theories generally. One is valence bond, crystal field, molecular orbital theory and also ligand metal theory. So ligand metal theory. So also is there. These are the four theories which will explain and which will develop the bonding in coordination complexes. And now let us see valence bond theory. So this valence bond theory introduced by Linus Pauling in 1931 to explain covalent bonding in molecules of main group elements. So this theory mainly explains about geometry, structure of the compound and magnetic properties and bonding. So these three properties was explained by this valence bond theory. So this was, who was introduced this one? Linus Pauling in 1931. So what he explains, covalent bonding. What is covalent bonding? Covalent is nothing but shared pair of electrons. Okay, in molecules. Main group elements is nothing but what here? Group elements is in periodic table. We are having D block elements. Okay. So P block elements, D block elements, S block elements, F block elements. So those elements, how this bonding is going to happen, was explained by Hitler and Pauling. Okay. So to adopt valence bond theory means to get this theory was adopted, means what here, for coordination compounds this theory explains about mainly what here, bonding. So how the valence bond theory, valence is nothing but what, the outermost orbitals. Okay, if you take carbon, the atomic number is 6, the valency is here 4, means what here, how the valence bond theory is going to coordinate in the coordination compounds, how it is related with coordinate compounds, means what is do you mean by coordinate bond or coordinate covalent bond? Here we are speaking about covalent bonding. So means what here, the coordinate covalent bond is also forming. So means what here, the empty orbitals. For example, we are having empty orbital and we are having filled orbital. 2 electrons. Filled is nothing but filled electrons. Okay. So here to the empty orbital, this filled orbital will give electrons to the empty orbital, and then what happens, it will get paired up. So by this what we can say here, this empty orbital is going to take the electrons from the ligand. So this metal atom, so this empty orbital indicates metal atom and this one indicates filled orbital indicates what here, ligand. So this ligand will donate electrons to the central metal atom, means what happening, the Lewis base and Lewis acid. So by this what we can say here, This is forming the coordinate covalent bond. So how the valence bond is forming coordinate covalent bond? So the empty orbital is taking electrons, or the filled orbitals donating electrons to the empty orbital to form a bond. That bond is called here coordinate covalent bond or day 2 bond. So this was explained by the valence bond theory. So now, so the bond is suggested what he told here, a day 2 bond is formed here. So means what here, a coordinate covalent bond is formed by the overlapping of a full valence donor. Donor is nothing but ligand, and empty valence orbital of the acceptor means what here, central metal atom. So coming to here, the vacant orbital. So vacant orbital, so then what happens in the first step, what we have discussed here, it is giving electrons. We are speaking about donor and acceptor. In the second step, what happens here, the vacant orbital will hybridize. So means what here, what is hybridization? The new equivalent energy of the orbitals overlap to give another new equivalent orbitals. That one we call it as hybridization. Okay. The vacant hybridized orbitals form new hybrid orbitals, which is equal to number of electron pairs to be accepted. Means what here, the coordination number to be same. So the vacant orbitals and the coordination number should be same. So means what we can say, what is the meaning of this point? Means what here, the vacant orbital, for example, here we are having, for example, here it is having some 3 vacant orbitals. For example, the filled orbitals is 3 we are having. Okay, the ligands is having 3. So here this one is the valency is 3. The outermost orbital is 3. And coming to here, the ligand, the coordination number is also same. So that is the meaning of this one. Means what here, the vacant orbital which is going to hybridize, and also the ligand whatever donating electrons, it should be also same. So means what, the coordination number and the number of electron pairs accepting for hybridization, that one should be the same. That is the meaning of this point. Okay. So the vacant orbital hybridize to form new hybrid orbitals equal to the number of electron pairs to be accepted, that is coordination number, and also vacant orbital will be the same. So this will decide about the geometry. This will say about the structure of the complex. Now next one. So now see here, the d orbitals means what here, the d orbitals which is involved in hybridization may be inner, outer or nd orbitals. So inner is nothing but what here, inner orbitals is nothing but n minus 1 into d. So means what here, penultimate shell. So the whatever orbitals going to give hybridization. What is hybridization? sp3, sp2, sp3d, d to sp3, dsp2. So these all come under the hybridization. So this may be involved in penultimate shell or normal d electrons. Outer means nd, inner means n minus 1 into the orbitals. So here we are having strong field ligands, weak field ligands, and we don't know how to identify what is strong field and what is weak field. So here we are having 4th group and 5th group. Okay, in 4th group we are having carbon, and in 5th group nitrogen and phosphorus. So these elements will undergo strong field ligand. And coming to weak field ligand, so weak field ligand is nothing but here oxygen, 6th group elements, 7th group elements. Okay, oxygen, sulfur, fluorine, chlorine, bromine, these all will come under the weak field ligands. Okay, so the strong field ligands will combine with weak field ligands will combine with strong field. So here, however we are speaking, see one thing you remember, this CNP and oxygen, sulfur, fluorine, chlorine, bromine. So these are weak field, these are strong field ligand. Okay, So coming to here, the strong field ligand, whatever we are taking here, so coming to here, the strong field ligand, so which gives the electronic configuration of the central metal ion, will cause forced pair by using Hund's rule. What is Hund's rule? Hund's rule is nothing but what here, once pairing of the electron completion only, then only we will enter into another pairing. So that is nothing but Hund's rule. So means what here, it will force electrons, means here it is undergoing inner orbitals, means this is the hybridization it is going to take place. So strong field ligands will undergo inner field, and weak field ligand cannot force the metal atom. Okay, so that's why it will undergo outer orbitals. So I think you have understood, strong field ligand will undergo inner orbital and weak field ligands will undergo outer orbitals. Okay, so for example, if you are getting D to sp3 hybridization, that one because of the presence of strong field, and if you are getting sp3d2, that is because of the presence of weak field. So this is the point going to explain. So here what happened, the strong field ligand will change the central metal ion, means because of the pairing of electron. But coming to weak field, it will not give configuration of the central metal atom. It will not force to pair the electrons. Okay, so by this what we can say here, the valence bond theory mainly explains about what here, magnetic properties and coordination compounds. Now let us see examples. So first of all, let us see the nickel chloride, tetrachloride. So here we are taking tetrahedral complex. In this, the name of this one is, here negative charge is there, so at the suffix we are getting 8. Okay, so the oxidation state of nickel is +2. What is the atomic number of nickel here? 28. So for the 28, the configuration will be, how we are going to get, argon, (3d8), (4s2). So this is the electronic configuration of the nickel without losing electrons. Okay, so coming to here, the configuration we are getting like this. This is the configuration we are going to write in ground state. So here what happens, what is the oxidation state of nickel? +2. So after rearranging this molecule, +2 means what? Loss of 2 electrons. But we are having -2 also. Okay, so coming to here, before rearranging, here we are, how much we are having? +2. So this +2 means what? Loss of 2 electrons. Out of 28, we are going to get only 26. Why? Because due to the loss of 2 electrons, it is giving the oxidation number 26. So Ni+2 ion. This is the configuration we are getting. And coming to here, after rearrangement is nothing but what here, after rearranging the molecule, so we are getting, so what I have told in the first step, what explains the valence bond theory? Coordinate covalent bond. So how it will give coordinate covalent bond? Here how many Cl4 minus Cl4 we are having? 4. So how many vacant orbital we are having? 4. So here first of all, Cl4 is a strong field or weak field? Weak field ligand. And coming to here, this one will undergo outer or inner because of presence of weak field ligand. So what happens? It will undergo outer orbital. So this will undergo only outer orbitals. So these are the outer orbital. These are the inner orbital. So coming to here, the 4 Cl minus ions, the 4 chlorine atoms will donate electrons to the empty orbitals of the nickel atom. So by this what it will give? It will give hybridization. Which hybridization it is giving? sp3 hybridization. Okay, so now how many unpaired electrons we are having? See in this we are having, so this is the hybridization it was described. And structure, we are what is the structure of sp3? Tetrahedral structure. Okay, then how we should identify the magnetic properties? So magnetic properties is nothing but what here? It consists of two types. One is paramagnetic, another one is diamagnetic. Paramagnetic is nothing but what? It should contain unpaired electrons. Diamagnetic means it should contain paired electrons. Now here we are having unpaired electrons. So these three are paired electrons. So any one unpaired electron is there, that one will be the paramagnetic. Everything should be completely paired, then only we will be getting diamagnetic. So now coming to here, see here, two unpaired electrons is there. So two unpaired electrons will give what here? Paramagnetic behavior. And due to the presence of weak field ligand, it is not forcing to pair up the electron. Okay, because of the weak field ligand, so what happens here? It is not going to force up. So that is the reason it is giving tetrahedral complex. Let us see next example. NaCN4 2-. Here what is the strong field? What is the weak field? So here CN4 is a strong field ligand. So why? Because I have told you group 4 and group 5, I mean 14th and 15th, carbon and nitrogen is a strong field ligands. So due to the presence of that one, it is a strong field ligand. Okay, so we have taken here, what is the name of this one? Tetracyanonucleate 2 ion. So now the oxidation state for this will be +2. The atomic number of nickel atom will be 3d8 4s2. Okay, so now coming to here, after losing of 2 electrons, this is the rearrangement we are getting. But here, due to the presence of Cn-, okay, so when strong field ligands comes, what happens? It will force to pair up the electrons from the central metal atom. Means what here? Here we are having two unpaired electrons. We should have to get paramagnetic behavior. But when you rearrange this molecule, after rearranging this molecule, how you rearrange it? According to Hund's rule, means what? Cn being a strong field ligand, the 3d electrons will get paired up and d orbital will come vacant. One of the d orbital will become empty. Why? Because these two electrons, one of this electron will jump to the another orbital due to the presence of strong field ligand. Because of that reason, it is rearranging in a molecule and getting completely paired electrons here. So then how many empty orbitals are left? 1, 2, 3, 4, 5. 5 empty orbitals are left. But how many bonds are there? Only 4 bonds we are having to coordinate with the empty orbitals. One is with D, another one is with S, another 2 with P. So by this, what is the hybridization we are getting? DsP2 is the hybridization we are going to get. Here number of unpaired electrons will be 0. Okay, why? Because all are completely paired. Completely paired means what is the magnetic we are getting here? Diamagnetic. Hybridization DsP2. Structure will be square planar here. Okay, so this is the structure of square planar. For this is for one is for tetrahedral, one other is for square planar complex. Now let us see octahedral complexes. So as I have told you, octahedral complexes consist of inner sphere and also outer sphere. Inner sphere is nothing but what here? See here, F is a weak field or strong field? Weak field ligand due to the presence of 17th group element. Okay, so coming to here, the weak field ligand will give outer sphere or inner sphere? Outer sphere. Why? Because it will not force the electrons to pair up. Okay, because of the presence of that one, it is not going to force the pair up. So now, if you take the cobalt atomic number is 27. Okay, so 27. So the configuration, how we are going to get? Argon 3d 7 4s2. So this is the configuration. So when you write the electronic configuration, this is the thing we are going to get. So here the oxidation state of, for everything you have to find the oxidation state. So for oxidation state of cobalt is what here? +3. So there will be loss of 3 electrons. 2 is from s orbital, 1 is from d orbital. Okay. So now due to the presence of how many F molecules is present? Total 6 F molecules. So due to the presence of weak field ligand, so what happens here? It is not forcing to pair up these electrons. Now these 6 molecules will donate electrons to the 6 orbitals. One is for S1 S and 3 is for P and another 2 is for D. So by this what we can say? So here sp3d2 is the hybridization we are getting, and the shape of this one is octahedral structure, and here it is a outer orbital complex we are saying. Why we are saying outer orbital complex? Why? Because it is a weak field ligand, and outer orbital complex is also known as how many unpaired electrons we are having? Total 4 unpaired. So that's why we say it is a high spin complex. Due to the presence of more number of unpaired electrons, we are saying what here? High spin complex. Then what we can say? It is a paramagnetic or diamagnetic? It is a paramagnetic behavior it is going to show. Okay. Next let us see octahedral complexes. Another example. So here before we have taken strong field. Now we are taking what here? Weak field ligand. So this is a strong field ligand. NH3 is a why? Because N is a 5th group element, and here 6 NH3 molecules is there. And coming to here due to the presence of strong field ligand, what happens? The electrons will pair up, means the vacant orbitals will be less here. Then what happens here? Coming to here, it undergoes inner orbital complex. Okay, so the electronic configuration of CO is this one, and losing of 2 electrons we are getting this one. Due to the presence of ligand, strong field ligand, what happens? They itself will get force up. So means what happens? They are completely paired. How many vacant orbitals we are having? Total 1, 2, 3, 4, 5, 6. So and also remaining 4. So coming to here, these 6 NH3 molecules will donate electrons to the 6 vacant orbitals. So means what here? 2 orbitals, here 1, here 3. Then hybridization we are going to get D2 sp3 hybridization. This is a inner orbital complex, and here we are not having no unpaired electrons. Then it is a diamagnetic, and coming to here structure will be octahedral. It is a inner sphere complex and also low spin complex. Why we say low spin complex? Due to the presence of NH3, a strong field ligand, it will force up the pairs, and because of pairing of electrons, they can participate in hybridization, which will accept the ligands. Okay, so these are the examples of the outer sphere, inner sphere of octahedral complexes, and here coming to here tetrahedral and square planar complexes. Now let us see examples. For sp3 we are going to get MnCl4, CuCl4, COCl4. These are the examples, and also NaCl4. And for square planar we are going to get the examples CuPt. And for octahedral we are going to get for outer orbital complexes FeF6, NaH2O. And for octahedral inner complexes we are going to get these are the examples. Okay, now let's see. So what we are saying, strong field ligands will force up to pair the electrons, but here there is a condition that what they are saying, not all strong field ligands will form the inner orbital complexes. Why? Because so due to the presence of strong field ligand is not going to observe. Why? Because if pairing is causes, there is a formation of inner orbital complexes after 4. Yes or no? If pairing is causes, what happening? It is forming inner orbital complexes, but it is not going to happen. Let us see one of the example. Here we are taking titanium. Titanium we are having only 2 electrons. Okay, and 4s2. After doing plus 2 electrons will be lost. We are having 2 electrons. But what happens? Cyanide is due to the presence of strong field ligand. It should face up to pair up the electrons, but it is not pairing the electrons, but it is giving the D2sp3 hybridization. Generally we have to get D3sp2 hybridization, but it is not getting like that. Why? Because here inner orbital complex formation is not required here. Why? Because here we are having only 2 electrons are already vacant here. Okay, so if there is no vacant orbital, then we can pair up. If it is already vacant orbital, because of the presence there is a available to form the hybridization, so because of that it is not taking the forced pairing. Okay, so this is the reason. And in octahedral with complexes like central metal atom D1, D2, D3 means always will undergo D2sp3 hybridization. Here these are the examples we are going to explain. This is the D2, this is the D1 and this is the D3. So these all complexes will undergo what here? Inner orbital complex. Why? Because they has the availability to form the hybridization. And nickel if you have been taken here. Okay, NaH2O6 2+. So in this what happens? H2O. H2O is a weak field ligand, water molecule. Why? Because oxygen is a weak field ligand. The configuration we have written. But what happens? There is no availability of d electrons. And what should happen here? It should give force to pair up electrons, but it is not forcing electrons. Why? Because here the O is a weak field ligand. It will give outer sphere mechanism. And if you compare this on what it is, what happening? It also should happen, but it is also not happening. Why? Because here, why? Because of the 2 vacant orbitals either in either outer or inner, there is no force pairing. Okay, because of the vacant orbitals is present, we can force up. Because of that reason it is not going to force up. So these are the examples, general examples he has explained, but he has not given correct explanation of the stability of the complexes. Now let us see what are his failures of valence bond theory. So it fails to predict a structure of 4 coordinated complexes will be tetrahedral, square planar, whether an octahedral will be low spin or high spin. So he is not giving correct explanation, right? He is saying that it is a low spin, high spin. But why it is low spin, high spin? We are depending upon the electrons, we are saying, but it is not giving correct explanation. Okay, and also he cannot give geometric like tetrahedral, distorted octahedral complexes. Okay, and also it neglects excited state in a complex. So excited state in a complex and cannot explain the spectrum. So valence bond theory cannot explain spectrochemical series and also excited state in a complex ions. And also it does not explain the calculation of bonding energy and also stability of the complex. What it is saying, only magnetic properties it is saying, only hybridization and geometry it is saying. It is not saying stability, it is not giving, and also bond energy it is not giving. Okay, it could explain only spin only magnetic moment, could explain. It could not explain the orbital magnetic moment. So it is not properly giving the importance of the ligand. So this is about the valence bond theory. In the next class we can discuss about the crystal field theory. Thank you.